All right, everybody, welcome to our first lesson in physics on circular motion. Now, you might be wondering, why exactly is Lucas not there? He's not on the screen. It's just a paper with the word circular motion written on him. And that's because, with the suggestions of a few of my fellow classmates, I have decided to take him to this new format where I just write the work and the formulas on this piece of paper, just so it's easier to comprehend with all the formula writing and math that comes with physics. So if you like the new style, be sure to tell me. So, feedback, it's always useful. And if you want me to redo my mechanics videos, because I know those involved quite a few formulas in this format, then I'd be happy to. Just let me know in the comments. So let's dive right in. So far, in the mechanics section, we've been studying objects that move in a straight line with a velocity in a straight line like this ball here. But what happens when you have objects that are moving in weird curvy lines, that are moving in like circles, for instance? That's what we're going to be studying here, objects that like to move around in circles, because what's happening is the velocity is inconstant. Because yeah, you could be moving, per se, at 30 meters per second around this circle, just constantly. But the thing is with velocity is that it's a vector. So it has both magnitude, that 30 meters per second, and direction. And as you can see, the direction when you're moving in a circle just keeps on changing. And so that means we need to use a different set of values when we're talking about circular motion. So the first set of values, the first value that we're going to talk about is angular displacement, or as I like to refer to it as little theta. That little theta there is angular displacement as measured in radians, or rads, as for short. Rads for short. And that's basically the angle of displacement. If you're moving in a circle, let's say you start here, and then you move up to here. Well, then from the center of the circle, the angle there is your angular displacement, your little theta. And that's pretty simple. Next, we move on to angular velocity, which is, its variable is a little omega, which kind of looks like a really curvy W there. And it is measured in radians per second, because angular velocity is just like regular velocity in that it's the change in your angular displacement over the change in time yields your angular velocity. And it's just how many radians you've covered in a certain time as you go around in that circular circle. And that's a pretty easy thing to understand there. And there's another formula we can use for angular velocity, which is 2 pi over t. Now what is t, you may ask? And that brings us to another value, period, which is t measured in seconds. And period is very simply the time taken to complete one full circle. That's t. And so 2 pi being the amount of radians in a circle, measured in radians, over 1 period measured in seconds, will of course give you your angular velocity. That just makes sense, right? Now there's one final thing we want to make note of here, and that is frequency. It's got a cursive F as its symbol, and it's measured in 1/second. And that is the number of complete revolutions per whatever unit of time. So it's not really 1/second here, it's 1/x. It can be 1/second, 1/minute, 1/hour. It really depends on what your unit of time is. And you can get frequency by taking 1 over your period. And that's pretty simple there. And those are the big units that we want to communicate there. Now, moving on. Those units kind of seem out there, right? We're measuring in radians. And this is kind of a new thing we're doing here, circular motion. So an easy thing that physicists like to do is relate it to the linear world. The linear world that we've been studying so far with our regular displacement, our regular velocity, our regular acceleration, all those things, right? Well, we can relate the circular and linear worlds through one simple thing, r, or radius, which, as you might imagine, is the radius of your circular track. Here's our circular values, so angular displacement, angular velocity, and a new value I'm going to introduce, which is angular acceleration, which you won't really use that often. It's little alpha, it's like that fish-looking thing there, and angular acceleration is simply equal to the same thing that linear acceleration is, except in angular terms. The final angular velocity minus the initial angular velocity over time. And it's measured in rads per second squared. And what did I mean when I said that radius is the connection between the circular and linear worlds? Well, the real connection here is that this little v here, our linear velocity, equals our angular velocity times the radius. And the same thing is true for the other. Our linear displacement is our angular displacement times the radius. Our regular velocity is equal to our angular velocity times the radius. It's a pretty simple group of formulas there that connect circular to linear world. And what that basically here is saying is you've got your radius and you've got your regular velocity, and that translates into your linear velocity, which is going to be tangential to your circle. Like that, or like that. And that is the connection between the two of those. Now, how is that important? Well, to discover the importance of that, first we're going to have to discover the importance of centripetal acceleration. Now, let's look here at the movement of an object. Let's say it's this little guy and he's moving in a circle, so he moves up here. And here's the center of his circular arc. And here's his angular displacement. There is the radius of his circle. And he's got two velocities. He's got his initial velocity here, and he's got his final velocity up here. Now, typically, if we use Newton's first law of motion, an object at motion stays at motion, this object would really want to just keep going in this velocity with that same magnitude and that same direction. It just want to keep going up, up, up. But something is pulling it inward, causing it to change direction. There's an acceleration that is happening, causing it to change direction, and that is centripetal acceleration. So if we take these two vectors and we add them, yeah, that's right, I said it. We're going to add them. If we add these vectors, here's vector 1, and if you remember the rules of vector addition, we need to take the tail of this vector and attach it to the end of this vector. And because it's moving in a slightly different direction, we're going to negative it. Negative. You'll see that the new resultant vector here, so here's vi, vf, vi, vf, and here's vres, the resultant, is going to end up pointing inward. And that gives us the direction of centripetal acceleration. Centripetal acceleration always points down in towards the center of your circle. Always. That is the constant direction of a centripetal acceleration. And now, let's see what centripetal acceleration is exactly. Well, we've got a very small angular displacement here, and so we can basically, and we know that we can equate that to our angular acceleration is the change in our angular displacement over the change in time. And we know that our typical acceleration here is going to equal the change in velocity over the change in time, right? And therefore, if we want to discover what this centripetal, what this angular displacement is here, we can determine that if you multiply that angular displacement using this triangle that we've made here, the angular displacement times the initial velocity, right, you can end up getting your change in velocity. Change in velocity equals the velocity, the initial velocity, times the change in your angular momentum. Now, what you say, how did you do that, Lucas? That makes no sense. Well, if you look, when I put these two angles together, the angular displacement here became this. Right there. And that, the change in velocity, is going to be our resultant here. That's the change in velocity as well, vres, right there. And our initial velocity here is this line. And if we just use our simple sine, cosine, theta rules, and you say this is theta here, and you multiply it by it, you end up getting that. It's just simple trigonometry. And that gives us this. Now, how is this useful? Well, if we assume that now we can say that our acceleration equals our initial velocity times our change in angular momentum over our change in time. That's a bit of a change up there. And then if you just want to simplify that, well, what do we know about change in angular displacement over change in time? That equals our angular velocity there. So now we know centripetal acceleration is equal to your initial velocity times your angular velocity. Bam! And we also know, we discovered over here, that velocity equals angular acceleration times radius. So what if you're going and you never really measured your initial velocity? Well, you can also calculate your centripetal acceleration using the formula the angular acceleration squared times the radius. Well, what if you never measured your angular acceleration? Well, we know that v equals angular acceleration times radius again. So if we want to rearrange there to get rid of our angular acceleration, we end up getting velocity squared over radius also equals centripetal acceleration, which is the formula you'll most typically see for this value here, our centripetal acceleration, which once again is measured in meters per second squared here, you will notice, because it's the meters per second up there that we're going after. And what can we determine using centripetal acceleration? Well, centripetal force. Whoa. And we know from Newton's second law that the force is equal to the mass times the acceleration. And for centripetal force, we just use centripetal acceleration. So that means centripetal force is equal to mass, in this case, times v squared over r, or mass times little omega squared times r. And that's your centripetal force. And this is the force that causes a body to move in a circle. Now, a lot of people get confused when talking about centripetal force. And why is that? A lot of people get confused because they think it's centrifugal force, which doesn't even exist. Now, what is centrifugal force, you may ask? Well, centrifugal force is the force that a lot of people believe exists that pushes things outward. Like, let's say you're swinging something, you're swinging a pail in a circle. Here's you. Hi. And you have a little pail attached to a rope, and you're swinging it over your head, and the water in the pail, right, it stays stuck to the bottom of the pail. It doesn't come out. And you think there's a force this way in the circle that points out of the circle that makes the water stick to the edge. But that is not true. In fact, there is no force that way. There's a force pointing inward. And that is your centripetal force, always pointing inward, just like your centripetal acceleration. And let's give a few examples to kind of get a hang of what that really means. So let's say there's an astronaut hanging out in space. Hey, buddy, he's our astronaut. He's hanging out in space. He's got a hold of a rope. He's got a hold of a ball at the edge of that rope, and he's spinning it. Well, the ball is in motion. It wants to move this way. It wants to stay in motion. It's its inertia. It wants to move that way because that is the vector of its velocity at that particular motion. However, there's a tension in the string that the astronaut is holding on. That tension applies a force, a centripetal force, that causes the ball to keep on moving in a circle. And we know that the formula for our centripetal force is mass times velocity squared over r. So, if the astronaut were to, say, increase the speed at which he was spinning that ball around, then the force of centripetal force would get greater. It would stress the string more. So eventually, that string would break. And what would happen if that string were to break? Well, the ball would follow its inertia. It would fly off in that direction, whatever direction its velocity was pointing to at that moment. So that it's not a centrifugal force, per se, that's causing the water to stick to the edge of the pail. It's the pail's internal inertia. It's the centripetal force that keeps the water from flying off in some random direction. Let's go for another example here. Let's say you're on Earth, and here's you, and you're holding up a little string. Your arm's freakishly long for some reason. You're swinging a ball around. Now, it's not going to work like it does in space. It's not just going to be in one dimension, because unfortunately here we've got a ball that has gravity enacting on it. And that's not really going to help your centripetal acceleration, because your centripetal acceleration is to the center, right? And that's going to push it down a bit. the horizontal component of your centripetal acceleration can be pushed down, so your rope is going to be at an angle. But you're still going to move in a one-dimensional circle, because the whole time your centripetal acceleration, the vertical component of it, will counteract gravity, right? But what if you're swinging it, let's say, here's another guy, and he's swinging it vertically? Well, we don't like to analyze these situations, us physicists, where they're swinging in a vertical ball, because unfortunately, in this particular instance, this velocity can never be constant, because sometimes gravity is acting with the centripetal force, both pointing down, but at the bottom of the loop, centripetal force is going up, gravity is going down. So you'll find that at the top of the loop, a ball will end up moving faster. The tension is no longer needed. It's just gravity that's keeping that ball moving, but at the bottom, the tension kicks back in. You may have experienced this on loop-de-loops. If you've ever been on a loop-de-loop in a roller coaster, that brief feeling of weightlessness at the very top of the loop-de-loop. And that's because the normal force, on a loop-de-loop, it's the normal force acting as the centripetal force. The normal force of the track against your cart. But up here, normal force is pushing down, but you no longer need it. Gravity's doing all the work for it. So that's that feeling that you get that gravity's bringing you down. And then it kicks back in, and the normal force is once again needed at the bottom of the loop. Moving on. That's just some examples explaining how our centripetal force works. Let's think about another one. How about the wall of death? Have you ever heard of the wall of death? That is a wall in which bicyclists, it's kind of like a circular cone track here, and bicyclists like to ride along the side of it. Now, what's keeping them on the side there? Well, if we were to analyze that with a free body diagram, let's say, and we've got a ball, not a bicyclist, I can't draw a bicyclist, and he's going along the side. Well, you know gravity's bringing it down, and the force of friction, being perpendicular to the surface, is fighting against that gravity. And then there's the normal force, which is acting as the centripetal force. So if the normal force equals the centripetal force, which also equals the mass times the velocity squared over the radius. Well, this explains the entirety of the wall of death to you. You see, the biker, if he's not moving at a fast enough velocity, he's going to fall. Now, why is that? And that's because the velocity needs to be big in order for the force to be big, in order for the normal force to be big. And because our formula for friction is the coefficient of friction times the normal force. In order for friction to be big enough to counteract the weight of the bicyclist, he needs to be moving fast enough to make the normal force big enough to make the frictional force big enough to counteract the weight. And that's really how the wall of death works there. Now, as you can see, centripetal force isn't really a set force. It's a force that can be many other forces. It can be the normal force, it can be the force of tension, and in the case I'm just about to explain, it can even be the force of friction. Now think about a car driving on a circular curve. Got Captain Car here, moving on a circular curve. What is causing that car to not just skid off the curve and crash into the side? Well, if we think about the forces acting on our car, you've got the applied force, which is bringing the car forward. And as the wheels turn, the direction of the applied force changes. Right? And it changes with the velocity. However, you've got friction acting against the force to the center. Friction is acting as the centripetal force. So in order to turn well, that requires friction. Now, then you'd ask, well, what about race cars? Race cars, their wheels are specifically made to be frictionless. How do they even turn? Well, that's because on racetracks, the track is angled a bit, kind of like that, so that any car driving on it doesn't need friction anymore, because now the normal force, a component of the normal force, is acting as the centripetal force. And that just makes it easier for race cars to drive. And that is really all when it comes to circular motion. So just as a quick recap, when analyzing circular motion, there are a few values you want to look out for. Period, frequency, angular displacement, angular velocity, centripetal acceleration, and centripetal force. Period is just time for one revolution. Frequency is 1 over the period. Angular displacement is just the angular displacement you've made when traveling in your circle. angular velocity can be calculated by angular displacement over time, or, if you're feeling like it, velocity over radius. And centripetal acceleration can be calculated quite a few ways, if you do remember, a few of which being just your velocity times your angular acceleration, or your angular acceleration squared multiplied by your radius, or your velocity squared over your radius, which is the one you'll see most often. And that is why when calculating centripetal force, we use mass times velocity squared over radius. And centripetal force and centripetal acceleration always point inward towards the center of the circle. And centripetal force can be made up of many forces. In some cases, it's friction. In some cases, it can be the normal force. In some cases, it can be tension. And in our next video, where we discuss gravitation between planetary bodies, we'll find out that it can also be weight.